you very much. I'm on, I think. I would like to talk about some ideas that came out from trying to understand what really, really large networks mean and how to handle them, and how far it goes in some interesting directions in mathematics. This is joint work with a lot of people, and I will not talk about different subgroups who prove different results to save time. So large networks, I'm thinking of, maybe you should think of some networks which are really large, like the internet, the social networks, ecological networks, or maybe a piece of a crystal, or a human brain is a huge network, or if you wish, the whole universe is just a single huge network of elementary particles. So now there are many interesting questions about huge networks, and I will skip even listing them. Just just the question of how they are given, how to run algorithms on them, how to get information about them, and so on, are all non-trivial mathematically. So let me, however, discuss just one issue. How do I assume that such a big network is given? So think of the internet. You will never be able to actually list all the nodes and all the connections between them and then store this in the memory of your computer, because first of all, because it's too big, and second, because the information is not really reliably available, and third, because it's not even well defined. I mean, there will be parts, so machines, who knows if they are working or not, and so on. So this is some issue. So I assume that the graph is huge, and I assume that it's not known explicitly. I don't even know the number of nodes. And as a mathematician, I would like to go to the extremes, so I will assume that there's absolutely no information available about the number of nodes. And of course, it's a meaningful question. What happens if you know maybe the order of magnitude or something? But what can we do if we don't even have information about the number of nodes? Now, this has been studied a lot, and there are two extreme cases where sort of a rather clean answer can be given, at least clean model can be set up. These are the dense case, when the graph has n is always the number of nodes, so constant times n squared edges, so a positive fraction of all pairs is adjacent. Or when the degrees are bounded, so when each node is only connected to, say, at most 10 others. So these two are, especially the dense case is quite well developed. It's a very good exercise case. And the bounded degree case is much less developed, and it's more difficult, and it has more applications, many more applications than the other. And then there is virtually nothing known in between. There is not even a good answer to the question how to specify such a network. Although, of course, there are many interesting examples. There would be many interesting examples. But the theory is not developed there. And I will talk about the dense case, because that's what is better understood. So in the dense case, we have constant times n squared edges, and here is how we access the network. Or the graph, we sample a uniform random node. We assume we can do that, and we repeat this a bounded number of times, so we maybe pick 100 nodes, and then we look at the subgraph that these induce, and from the properties of this subgraph, we would like to conclude properties of the big networks. And this is a model. It's an extreme model, sort of minimalist model. but it has many interesting properties. Now, this is a math audience, so I would like to show how you go off in a mathematical direction from here. But it's very interesting to see what kind of algorithms can you design based on just this information. And there's a highly non-trivial area of computer science which is called property testing. That's lots of people, some people who contributed to this here are listed here. And it turns out that it has many non-trivial algorithms that you can develop in just this very simple model. So this is some kind of statistics. You have this big graph and you can sample from it. And from the sample you would like to conclude that the big graph also has properties. But I would like to go off in another direction. And this is about approximating dense graphs. So suppose you have a huge big network. And now it's so huge that I cannot gather the data at all about it. So I would like to make some model of it that I can handle. So how to model such a big network? What does it mean to model it? And there are two possibilities. One, you might want to model it by a smaller graph. So you would like to pick a smaller graph such that this smaller graph is approximately, has approximately the same properties as the big graph. What does it mean approximately? Well, I mean, some things you can think of, like maybe it has the same density of edges, for example. The big graph, 1/3 of the pairs are connected. That should be true on the small graph also. And it turns out that this really leads to the theory of semi-ready partitions and regularity lemmas, which I will not introduce here except in some very informal way. But it's a very, very important method of dealing with large networks. And the other thing which I will talk about more is how to approximate a large dense graph by an even larger graph. Now, what does it mean by an even larger graph? Well, maybe infinite graphs. If you think of infinite objects, now you might think that that makes no sense, but think of the following. So think of a piece of a crystal. That's a very large graph of atoms and bonds between them. Now the way, that's the way maybe a chemist think about it. But if you are an engineer who wants to build a bridge from that metal, then you will not think of it as a large network of atoms or large graph of atoms. You'll think of it as a continuous material that can be deformed or stretched, that has maybe a heat distribution over it. So there are all sorts of various continuous functions that describe the relevant properties of this piece of metal. So in this sense, it's good to approximate this finite but very large object by an infinite but nicer object. And this is what we would like to do. And this leads us to the theory of graph limits. So, but first I would like to explain some notation or some illustration. So here is a graph G. It's not a large graph. It's a decent small graph. But already this is pretty dense. It's very difficult to really make. I mean, you look at this picture, so what does it tell you? Not much. It's usual you can associate with it the adjacency matrix. Rows and columns correspond to the nodes, and there's a 0 if they are adjacent here, and it's a 1 if they are not. And that's even maybe less clear what it means, this picture. So I certainly make sense to make it a little bit more visible by replacing the ones by little black squares and the the zeros by little white squares. And I consider this to be the whole thing inside the unit square in the plane, this geometric picture. And I call this the pixel picture of the graph. So I pick the origin on the upper left corner because it comes from a matrix. And that's where matrices put their origins. So, okay, so I get here this picture, which I consider as a 0, 1 valued function. So the white means 0, the black means 1, and it's a function defined on the unit square. Now, if you do this on a bigger scale, here is an interesting graph, interesting in the sense that it has no feature. This is a random graph on 100 nodes. So these little pixels are randomly black or white except for the symmetry. And now from a distance, and with, it always depends on the projector, but this should be sort of gray of the same average darkness as this side. And if, of course, if I increase the number of nodes, it looks more and more just uniform gray. Here is another example. This is a graph which you get this defined by this chessboard. And if you look at it, then of course this should also look like uniform gray, except you don't somehow doesn't come out. If you make it dense enough. But that's not the right way to think about it, because if you rearrange the rows and columns, you bring the odd nodes first and the even nodes later, then you get this picture, and it's pretty clear that this tells you the truth. And so you have to be careful with looking at these pictures, because rearranging rows and columns changes the picture. Now, if we go back to the random graph, it's not hard to argue that no matter how you rearrange the rows and the columns, even after you have generated the graph, it will look gray. There is no way to make it anything nicer. Here is another example. It doesn't matter how it's grown. It's some graph that is grown by some rules that are popular. And it's actually a very simple rule. You add either a node or an edge at each time, and the node is just added, it's isolated, and then you add edges connecting it to the rest. And also at any point, you either connect two new nodes, two nodes which have not been connected, or you create a new node, and you adjust the probability so that the density stays constant. And then you get this kind of picture. Clearly, the later nodes have fewer connections. And if you, OK, so this is an example. I'll come back to this. And now, let me come back to this approximation by smaller. It's a famous regularity lemma, which I will give a very informal explanation, which just, since I have these pictures here anyway, I will try to explain it. So this is a graph, I mean, in this pixel representation. Well, it looks like gray. There's not much structure in there. But I rearranged it a little bit, and now you see some sort of structure. I mean, this corner here is clearly not as dense as this other corner, opposite corner. And these are sort of in between. So somehow this structure can be formulated as cutting this up into 4 parts, and then in each part averaging out the grayness, and you get something like that. So this picture tells you what the structure here is. And this picture is a much simpler picture. It's just specified by 3 real numbers, 3 densities. The essence of Semiredy's regularity lemma is that you can always rearrange the nodes, so that if you cut it up, then you get such a picture. And moreover, this contains everything that you can obtain by rearranging the rows. So if you pick one of these parts, then that is already random-like with a certain error. So you can, inside here you would not gain anything by further rearrangement of the nodes. So you can cut it. So after the rearrangement of the nodes, you can cut it up into some number of parts so that each part looks like random with different densities. And this is actually, I will not state the formal statement, in particular because at least there are at least 3 different versions, which all have their merits. But the point is that this principle that if you have a very large structure, you can understand it by decomposing it into a kind of structured part which contains just these 3 real numbers. That's all the structure there is. And then if you want to go back, then, well, there is a little error, and modulo this error, you just do random in each of these with the appropriate density, and then you would get a picture which is very similar to this. So this applies in a far greater generality than just graphs, and it has been applied to sequences of numbers and to hypergraphs and to a lot of other structures, and it's a very powerful tool. Okay, so this is approximation by smaller, and of course you may think of, why do I want to approximate this picture by such a picture where by this kind of step function? Why not by some other function which might approximate it even better? And that's the next idea. And for this, I have to introduce the notion of graph limits, and let me try to explain a little bit what motivates. One example that motivates why graph limits are useful. So what is a graph limit? So we have a very large graph, but we're not satisfied that it's large enough, so we assume that its size grows to infinity. So there's a sequence of graphs, and we would like to associate a kind of limit with this sequence that will represent those properties of these big graphs which are relevant for us. So we somehow would like to define a completion of the set of graphs. We would like to define when a sequence of graphs is convergent, and if it is convergent, we would like to assign a limit object to the sequence. Now, why is this good? Let me give you one motivation to which I will come back. So let's look at a very classical problem. First-year calculus problem, minimize this function over the non-negative numbers. And of course, you already have found that the minimum is attained at square root of 2. So it's not attained in rationals. So if you are in ancient Greece and you don't accept any other number except rationals, then you would say that this minimum is not attained. You can get arbitrarily close to it, but the minimum is not attained. And let's just say that this implies that real numbers are useful. It justifies the existence of real numbers. Let's look at a graph theoretic extremal problem. Minimize the density of 4 cycles, cycles of length 4, in a graphs where the density of edges is fixed at 1/2. Now, this you will probably not do in head, but one can prove, it's not hard to prove, that this density is always at least 1/16, and it gets actually arbitrarily close to 1/16 if you take a very large random graph. But it's always strictly larger than 1/16. So the minimum is not attained among graphs. So it's a situation is similar, and here we took the completion of rationals, and here we take the completion of graphs, and then the minimum will be attained, and that's very convenient. And that's one reason why graph limits are useful. I will show you other examples. So what are these graph limits? I'll show you a few examples. So I told you that a random graph looks like uniform gray. So this is with density a half. So which depends on the projector, but there should be a density about 1/2. But its grayness should represent this. And in a sense, this means that if we take the 1/2 function on the unit square, then this will be approximation of this. And this should tend to this function if the number of nodes tends to infinity. Again, you have to be careful. This does not tend, these chessboards do not tend to the 1/2 function because they are actually all tend to this function. So here is this randomly grown uniform attachment graph. This graph, if you look at it from a distance, you will see that it should actually tend to a function, and you can figure out that the function is given by the formula 1 minus the maximum of x and y. So somehow this function should contain all the information that we want to know about this huge network, the huge graph. So this huge graph looks essentially like this function and a random noise. Now, what does it say? In what sense should that contain all the information you may want? So let me give you an example. For example, if you want to compute the density of triangles in that left-hand side graph, then it's not hard to see that it can be expressed or approximated by just an integral on the right-hand side, where you see the triangle appearing here, so there will be a variable for each node of the triangle, and the function is w on the right-hand side. You get this integral. So if we know that approximation, then we know this graph also well. Now let me just tell you a little bit about the math of these limit objects. So first of all, define this for any two graphs, f and g. I define by t f g the following probability that you map the vertices of f into the vertices of g randomly, and what's the probability that the edges are mapped onto edges? Some number. And now I say that the sequence of graphs where the number of nodes is growing is convergent if for every f this number is convergent. This has a limit. So the edge densities have a limit, the triangle densities have a limit, and so on. Now this is equivalent. I mean, this is mathematically a more convenient definition, but it's not hard to see that it's equivalent to saying that if you take a fixed k and you take this sampling method that I described at the beginning, you sample randomly k nodes and look at the subgraph that they span, then this gives you a probability distribution on graphs with k nodes, and these probability distributions should be convergent for every fixed k. That's equivalent. So in other words, sequence of graphs is convergent if in our model they are becoming more and more similar, because the sampling will distinguish them less and less. Now, I hope that the pictures convinced you a bit that what the limit objects should look like. They should be functions defined on the unit square with values between 0 and 1. They should be symmetric and they should be measurable. And I denote this by W sub 0. So this is, these should be the limit object. They are called graphons somehow. Now, so remember this TFG was the density of F in G. It's expectation that a random map preserves edges, or the probability. And we can generalize this to any such function by this integral formula. So we associate a variable to each of the nodes, and we, over all edges, we take the product of Wxi xj, and we integrate this over the unit cube, I mean VF dimensional cube. So this is the definition of this thing. I'm sorry, this is how to get rid of this. Okay. So this is the expectation of this. And so this is the definition. And the nice thing about it is that it really extends the previous. So if I put here this chessboard-like function that I associate with a finite graph, then I get the previous notion of a density. It's easy to see. Now, here is the definition. I say that a sequence Gn converges to W if for every finite graph F, the density of F in Gn converges to the density of F in W. It turns out that this is a good definition. I will only mention a few of the important properties. So first of all, for every convergent graph sequence, so if these numbers converge to anything at all, there is such a function which represents the limits, so that the graphs converge to this function. Now, you may actually wonder at this point that measurable functions, this is really a big class. And you might think that maybe, I mean, finite graphs are so simple objects that their limits should be representable by something simpler than measurable functions. Maybe piecewise linear functions, maybe something else. But no, the answer is that for every measurable function, you can construct a sequence of graphs which has this limit. Now you may still say, okay, but maybe this limit can be represented by different functions, which is true. Okay, so it can be represented by different functions, but the answer is no, this limit is essentially uniquely determined up to a measure preserving transformation in the variable, which is a technical complication here, which I will just mention. But so basically, it's essentially it's unique. It's essentially unique. So this is these are sort of the main facts here that say that these definitions work. So you can associate such a limit object to any convergent graph sequence. It turns out also that in an appropriate topology, this is a compact space, and so everything is nice. And, you get all right. So let me now go to applications of this in math, in particular in extremal graph theory. And for that, I would like to start with reviewing some classical results in extremal graph theory. So the first extremal result in graph theory was probably proved by Mantel in 1906. But it's a very special one, and then Turan's theorem, it's known under Turan's theorem, which is a much more general statement, but let me just formulate this special case. So it says that if a graph contains no triangles, then the number of edges is at most, well, that's roughly half of all edges. If n is large, this is about half of all edges, so the density of edges is at most a half. And the extremal graph is obtained when we split the nodes into two equal parts and put every edge in between them. So this is really the chessboard example. There is a stronger theorem from the 1960s by Goodman, and that says that if you look at the number of triangles in a graph where m is the number of edges and n is the number of nodes, then the number of triangles is bounded by an expression where the crucial thing is that there is this 4m over n squared minus 1. So if the number of edges is larger than n squared over 4, then all three factors here are positive, and therefore there is at least one triangle. Here is another classical result. This is also a very special case of a much more general theorem, which says that, which bounds the number of triangles from the other side. If the number of edges, you can write any number in the form k choose 2, where k is some real number. And then it turns out that the number of triangles is bounded by k choose 3. And it's, of course, very suggestive that the extremal graphs look like you take k nodes, supposing k is an integer, and then you put a complete graph on these k nodes and no other edges. So just have isolated nodes to the right number. If k is not an integer, then the Kraskov-Katona theorem describes exactly the extremal graphs, but I will not go into this now. So let's put this in a little bit more general context. I hope you can see that this has different color from this. So what happens here is that for every graph, I take the density of triangles, so just the fraction of triples that induce a triangle, and the density of edges, the fraction of pairs which induce edges, and I put a point for this in the unit square. So these are two numbers between 0 and 1. Now if I do this for all graphs, then I will get some part of the unit squared filled. It turns out that this will be dense in a part, these points, and other parts will be empty. Now, what do we know about this shape? First of all, this Kraskov-Katona theorem, the one that bounds the number of triangles from above, gives here this curve. It turns out that this is the x to the 3/2 curve, so it's a nice curve. And and this curve is now there will be some points on this curve which are achieved, not everything, but they will be everywhere dense. So this curve really is the boundary of this region. Now, what about the other side? Well, first of all, the Mantel-Turan theorem says that after 1/2, you don't, it goes up. It just says that after 1/2, you don't get any points on or near this curve. But the Goodman theorem gives a very nice bound. It tells you that if you look at this parabola that goes through these 3 points, then this is a lower bound. So everywhere, all this area, this region will be above this curve. Now, you get some points which are exactly on this curve, and these are for the edge density being 1/2, 2/3, 3/4, and so on, and they correspond to graphs where, so the 1/2 corresponds to this graph where you split the points into 2 equal parts and take all edges in between. The 2/3 will correspond to when you split into 3 equal parts and take all edges in between, and so on. So these special points, there's an infinity of them converging to the corner there. They are all on this parabola. Now, the first guess would be that, well, in between, well, maybe for number theoretic reasons, you cannot get it exactly, but maybe you get arbitrarily close. But the answer is not. And it was a big surprise. Bolobash proved that is in 80s that this maybe late 70s, that if you draw the chord between 2 of these special points, then of course the parabola is below the chord, but all the other points are above the chord. I mean, all the points you get from graphs are above the chord. So this region is above the chord. And with Miki Shimonovich, we formulated actually a conjecture of how these curves look like, and we proved that the conjecture is true in a very small interval around 1/2, but actually around each of these special points. But so it was very likely that this is the truth. Actually, these curves are cubic curves. There are some kind of elliptic curves here that connect these 2 adjacent points. I mean, this is a cubic curve also. And now this conjecture was proved first for the first interval by Fisher in the 90s, and then Razborov proved it in 2006 for all of these curves. And since then, this result has been extended to prove similar bounds for the number of complete R graphs for any R, and so on. But certainly this tells you that even if we look at just these 2 special graphs, then the picture can get quite complicated. And it's a difficult question to figure out the possible density relation already for these 2 graphs. By the way, the method of Razborov then turned out to be quite successful, and there are many recent applications to other problems in extremal graph theory, about which I will not say more. Now, let's see. So let me jump from this very special case to some general questions. So here we looked at just the densities of edges and triangles. Now suppose you want to know about the densities of 5 cycles and the densities of complete graphs on 10 nodes and so on. How are they related in a graph? How are these numbers related? So we can ask which inequalities between these subgraph densities are valid. Maybe linear inequalities, maybe algebraic inequalities, which of them are valid? All these proofs really somewhere down there work with Cauchy-Schwarz. You do some counting and apply Cauchy-Schwarz and 15 times, and then you prove the result. So it's a natural question whether all such inequalities can be proved using just Cauchy-Schwarz. And then the last 2 questions I will not come to. You would like to understand also the structure of extremal graphs, and it's actually, maybe I left it here because that's what we are working hard on with Balázs Szegedi to try to answer the last question, but but I don't think I will be able to get that far. But anyway, let's look at the first question here. Which inequalities between subgraph densities are valid? So let me first introduce some notation. So this is just a convenient formalism. So I will look at formal linear combinations of graphs with real coefficients, and I call this a quantum graph. Now, I've been criticized often that this is some, you shouldn't use this kind of catchy words. This actually comes from quantum physics. So the first question where this was applied was actually a question of Mike Friedman coming from quantum physics. So there is some justification to the name. OK, now a graph parameter is just a function on graphs which is invariant under isomorphism. And if f is a graph parameter, then I will extend it to quantum graphs just linearly. And now, if x is a quantum graph, I say that x is greater than or equal to 0 if x is a quantum graph. I say that x is greater than or equal to 0 if txg is greater than or equal to 0 for every graph g. So this is really a linear combination of subgraph densities described by this x. And so we would like to know what graphs have this property. And in this formalism, Goodman's inequality can be written like a triangle minus twice a double edge plus a single edge is greater than or equal to 0. If you plug this in and rearrange, you get exactly that statement. Or the Kraskal-Katona theorem can be written like two disjoint triangles are always better than three disjoint edges. Now, some inequalities have a nice way of deciding them. And here is a theorem. I wrote Bolobash here, although he only proved it in a special case, and then I don't know, maybe Schelp and Thomasson formulated it more generally. But anyway, so this is a very nice statement. It looks at a x which is a linear combination of complete graphs. So we are interested in linear inequalities between densities of complete graphs. And then the statement is that this is greater than or equal to 0. So that means the density is non-negative for all graphs, if and only if it's valid for all complete graphs. This is not trivial why complete graphs here should influence complete graphs in the other one, but this is true. And in particular, what it means is that, say, coming back to, you take any linear combination of these two that corresponds to some kind of linear objective function, and it says that this is non-negative over the whole region here, if and only if it's non-negative in these special points. They correspond to the complete graphs. So in other words, this gives that this region must be above these chords in particular. So this you can rewrite in, the density in of a complete graph in a complete graph is easy, and you get this formula, which is a simple algebraic condition. And in particular, this can be easily decided, in fact, decided in polynomial time whether such an inequality is valid. So if you come to me and give me a linear combination between densities of complete graphs, and you say you suspect that this is true in every graph, then by a simple computation, I can verify whether you're right or not. Let's go to more general questions. So suppose X is now an arbitrary quantum graph, and you would like to know whether X is greater or equal to 0. Let me spend a couple of minutes on explaining that it turns out there is a very strong connection with non-negativity of multivariate polynomials. Now, there are many relevant results here. So first of all, there is the famous Hilbert problem, which says that, what does it, so we have a multivariate polynomial with real coefficients, and we would like to know whether this is non-negative for every substitution. Clearly, if it's a sum of squares, then it has this property. But Hilbert already knew that this is not if and only if, and he conjectured, and then Artin proved that, in fact, the characterization is that it's a sum of squares of rational functions. It's a famous theorem. And from this, it follows, and also from general results of Tarski, it follows on decision in real arithmetic, decidability of real arithmetic, then that if you give me a multivariate polynomial and you ask whether it's non-negative for all values, then I can decide it in finite time. There's a decision algorithm for that. And, but if you are interested in just deciding whether it's non-negative for every integral substitution, then this is undecidable. And that follows from Matyasevic's solution of another Hilbert problem. So the two Hilbert problems altogether map out the picture here. And the question is now, is this question more similar to real multivariate polynomials, or to multivariate polynomials, real substitutions or integral substitutions? And the answer is the beautiful result of Hatami and Nurin, which says that actually this is undecidable. So you give me a linear combination of subgraph densities, let's say with rational coefficients, so that they are actually explicitly described, then there is no decision algorithm to decide whether it's true or not. I can't resist to show you the basic idea of the proof, from which it's still a lot of more, but this is the basic idea. So the question is, so they reduce it actually to the Matyasevich result. So in other words, they say that here is a polynomial, say with integral coefficients in many variables. They construct for it a graph as a linear combination of graphs, such that this is non-negative if and only if the polynomial is non-negative for all integer substitutions. How do integrality of the variables come in? It's the following. So the variables will represent sort of subgraph densities. Now, subgraph densities can be any rational number. So this is not, if you go to the closure, then it's any real number. But they use the Bolobash result. So here is this region, and let's write up a condition on the graph G, that the density of triangles minus the density of edges plus pairs of edges plus the density of edges is 0. So that means in Goodman's theorem we get equality, and by Bolobash's result that only happens in this discrete set. So which means that this forces the edge density here to be of a special form, 1 minus 1 over k. So after a simple transformation, it becomes an integer. And now, of course, you still have to build a lot of other graphs around so that all these densities are combined in a single polynomial and so on. So the rest is still a hard work. But it's a beautiful way to somehow discretize the problem and get this proof. So that's how they prove it. And but it turns out that, on the other hand, it is decidable with an arbitrary small error. We have Balázs-Szegedi result. So that means that you can somehow have an algorithm which will tell you either false or true. And the algorithm, well, if it's false, it will tell you false. And if it's true, then it might still be false, but it will not violate very much. So for every epsilon, it will be violated by at most epsilon. So you can have such an algorithm. So I will come back to that, but let's first talk about this Cauchy-Schwarz issue. So let's do some computation. So I will look at graphs which have some number of unlabeled nodes and some number of labeled nodes. And labeled nodes, k labeled nodes. And I think of these as the points where they communicate with the outside. And this is sort of their internal structure. And then I can, again, construct quantum graphs as a formal linear combination of these graphs. So I can look at all k-labeled quantum graphs, form a linear space. I can think of these as somehow there are the labeled nodes which I see, and there is some gray area there which I don't see. Now we can define a product on this by taking the union. So if for two k-labeled graphs, take the union, and then I identify the labeled nodes, and that I call the product of them. And then I extend it by linearity to all quantum graphs. Now if, again, every graph parameter I extend linearly, and okay, I just repeated here the definition. So, okay. Let me now do some computation with this. So let's look at this. So these are labeled nodes. So there are no unlabeled nodes, and I take this formal linear combination, and let me square it. So what happens? Well, it turns out, I mean, this is nice. You get back the same thing. For example, there will be the square of this, but that means you have to glue it together with itself, so that just gives the triangle. But you get also the triangle with a minus here and so on, but things cancel and you get the same back. Let's do another exercise. Let's look at this graph here, and let's square it. Well, we get some junk here, some expression here, and I also it seems I multiplied it by 2, which I forgot to put here. So it's twice this square. Now let's add up the two things. So I add this up. I get this expression there on the right-hand side. And now what I do here is I forget about labeled or unlabeled, so I just erase the labels. And I also forget about isolated nodes. I don't like them, I forget. And then I can get some cancellation. I get exactly the Goodman expression. So Goodman's inequality, which says that this is non-negative, is true because I just wrote it as a sum of squares. Okay. Now the question is, is this a valid proof? It turns out that it's a valid proof. So, so you get, so you can prove that if this computation gives you some expression, then it's always non-negative. That's not hard to prove, of course. You just have to understand what it means. But after that, I can translate this Cauchy-Schwarz question into like Hilbert's problem. Are all non-negative quantum graphs square sums? And we more or less already know that the answer is no, because if all non-negative quantum graphs are square sums, then the question of non-negativity would be decidable. You could just, make two Turing machines. One would look for a counterexample, and one would look for a representation as square sums, and eventually one of them wins, and that's a decision algorithm. So anyway, this is the exact formulation of this, that it is true that if a quantum graph is a sum of squares, then it is, after ignoring labels and isolated nodes, then it is non-negative. And the question is, suppose that x is 0, so let's call these square sums. So is it necessarily a square sum? And so we know that the answer is no by Hata-Minorin. In fact, you cannot prove all valid inequalities by any means. So the next question would be, okay, so what is the analog of a rational function squared? But no such representation can exist, because each of those would give any of those would give a decision algorithm, and we know that it's undecidable. But it turns out that x is non-negative if and only if it is in the closure of square sums. Now, what does it mean, closure of square sums? Well, square sums form some subset, some linear subspace of quantum graphs. And if you close this in, say, L1, then you get exactly the non-negative quantum graphs. So there is some positive fact here. This is not... This also takes some work. It's based on semi-definite duality, semi-definite optimization, and that can be applied here to prove this result. There are so you might wonder, okay, I mean, so it's approximately and so on. Does it have any practical use? So it turns out that this group of people who works around Rasborov, and they are solving one old problem after the other, so very successful. They actually use this semi-definite optimization for concrete examples. So it turns out that writing x as a approximate closure of square sums gives some bounds, and then those squares have to be very small, and that gives information about the structure, and then you can work out this information and prove results along these lines. It's a lot of hard work, including some computation with semi-definite programs, but it's very successful. It has solved several long-standing open problems. Another remark here is that there is a similar result about polynomials, which is fairly recent, by Lasserre, which exactly sounds like this. A polynomial is non-negative if and only if it's in the closure of square sums. No, independent. Actually, he did it maybe a year or two earlier, but earlier than we published this. So okay. So this is. So I think this should show that looking at this way at graphs, one gets some quite general questions that otherwise are not even formulable. You cannot even formulate them without using partly these algebraic techniques of quantum graphs, and then behind this is really the limit space where you do the work. So this is the proof of this really is depends on Hahn-Banach theorem in the limit space. You have to go up there to do this. And I think I'll stop here. Thank you.